particular example, I'm going to talk about another concept related to rational functions. We already discussed vertical and horizontal asymptotes. In this one, I'm going to discuss a concept known as wholes. And I'll get to in a minute what wholes are exactly, but let's take a look at this. This particular rational function, it looks like it could be kind of complicated, but it's not that bad. It turns out the top part is factorable. And if you use x factor on this top part, what you get is x plus 5 times x minus 7. And that's important. It's very important that we do factor that. On the bottom of this rational expression, we get x plus 5. And I want to remind you that whenever we have a fraction bar, there are implied parentheses around the numerator and the denominator. Implied parentheses. That's always true on fraction bars. Now, because we have a common factor in the numerator and the denominator, we can cancel. So I'm going to go ahead and cancel the x plus 5 and the x plus 5. And what that leaves us with is just y equals x minus 7. So maybe when you first were looking at this, you thought, ooh, this is going to be tricky. But in the end, it's not that difficult to graph. It's just y equals x minus 7. There's only one little problem, and the little problem is this. It's this denominator. In the original function that we were given, we have an x plus 5 in the denominator, and that means that our domain is limited and that x cannot equal some number. I want you to think about it for a minute. Do you know what the number is that x cannot equal? Hopefully you guessed that x cannot equal negative 5. Now for that reason, when we go to graph y equals x minus 7, there's going to be a hole in the line that we get. So here's x is negative 1, negative 2, negative 3, negative 4, negative 5. At this point, there's going to be a hole in the line. So x minus 7, y equals x minus 7, that has a y-intercept of negative 7, which is 1, 2, 3, 4, 5, 6, 7, way down here. And then it has a slope, a rise over run of 1 over 1. So we kind of go up like this, up like this, up like this. To get the rest of this line, what we do is we simply go down and to the left, and I'll keep doing that as far as we need to go. And then let's go ahead and graph this line. So here's what the line looks like. The only thing is that we're going to have a hole at this point. In other words, this line is complete, and every xy ordered pair on this line is a valid solution for this equation. However, except for x cannot equal negative 5. So we're going to have to find a way to show that there is no point here at negative 5. And the way we do that is we put an open dot right here. So let's go ahead and look at x equals negative 5. We'll just put a little open dot right here. And by putting that open dot there, that indicates that, again, that there is a hole in the line at x equals negative 5 because our original function did not allow there to be an x equals negative 5. So for that reason, when we go to graph the function with the cancellations, we have to put the hole. And I'm going to go ahead and put the word here so that you can have it for your notes. That guy is known as a hole. And there can actually be more than one hole in your graph depending on what you have in the denominator here.